So now you're in the twilight zone. Why are you in the twilight zone? Because this experiment is not going to be conducted hands-on, thanks to the coronavirus. So, we've got to use your imagination. You've got to be able to think the experiment, which is something that Albert Einstein used to do constantly. He was famous for thought experiments. But in this case, I'm going to describe the experiment, which is, in this case, calorimetry, and the theory behind it, the types of calculations that you'll need to do, and then I'm going to give you the data that you would need to do those calculations. The data was actually gleaned by a former or previous class of CH213 approximately 1 year ago. We went into the lab and gathered this data. So it's real data, and I'll show you that later. But first, as a point of review, what is calorimetry? Well, calor is a Latin word that goes along for any of you who have had anatomy and physiology, understand the 4 classical symptoms of inflammation. Calor, rubor, dolor, and tumor. Right? Tumor is swelling, dolor is pain, rubor is red color, so you see the redness around an inflamed wound. The one we're interested in is calor, which is heat. Inflammation causes an area of your body to become warm. So there you have calor, and it's combined with the word for metric, which means to measure. So all calorimetry does is measure heat. How much heat is being transferred in any process. And we need a special device to do that. Okay, so the device we're going to use is called a calorimeter. There are various types of calorimeter that are available. You can buy them from science supply houses, and I have a whole set of them on the New River campus that I never use because I don't need them. They're overkill. I like to keep things simple. And in our case, it's going to be extremely simple. All you need is a vessel that holds the reactants and measures any temperature change. It's that simple. So, remember in the lecture how I described the difference between a system and surroundings, right? This is just a matter of review. So you have system, surroundings, and if we don't confine the systems and surroundings, the systems is whatever the reaction defines it to be, or whatever we define it to be, and then surroundings is everything else in the universe, right? But that's very often not convenient. We need to define what our surroundings are and put limits on them, right? So these will be our surroundings. Now, the boundary between systems and surroundings can be one of 3 types. It can be open. Let me write that over here. Let's just do away with this. I got a small whiteboard here, which doesn't give me much room. Okay. So that border can be open, which means matter and energy can flow in either direction, right? It can be closed, in which only energy can flow. All right? Or, in our case, we want a border or boundary that gives us an isolated system. Right? An isolated system is one in which matter and energy cannot cross the boundary. Right? So what's key to using calorimetry is that our device creates an isolated system and neither matter nor energy can cross the boundary of our calorimeter. In our case, our calorimeter is going to be made of styrofoam cup inside a styrofoam cup. Right? That's to give us double insulation. So styrofoam is an extremely efficient insulator. So when we double it up, there's nothing getting across that boundary, as long as it's water-based. Right? Because anybody who's ever used a styrofoam cooler knows you don't spill lighter fluid, gasoline, any hydrocarbon like that on your styrofoam, it will immediately melt it. Right? So the types of reactions we can conduct inside this calorimeter must be water-based. And fortunately, all of our the parts to our experiment today are water-based. Okay, so we've got the cups. We're going to have a lid, just a simple polystyrene lid, and then we're going to have a hole in it, right here. And into that, we have a thermometer. That's how we measure any temperature changes. Now, the original design had a stirrer built in so that you could mix it. But the stirrer was not very robust. It would corrode over time, and it just created too much trouble. So what you would normally do in a hands-on experiments, in this case, would use your thermometer to stir the mixture. And if you're careful, they're robust enough, you can stir with your thermometer. The other thing that does is it limits the ability of the calorimeter itself to absorb heat or evolve heat, right? Because the calorimeter has a heat capacity of its own. And we'll take that into account when I show you calculations. All right, so there's our calorimeter, and inside the calorimeter, we have an isolated system. Right? So what does that mean in terms of actually performing the experiment? All right. So what that means is, in an isolated system, any heat, we use Q for heat, remember? Any heat change that takes place inside the calorimeter between any of its components, everything has to add up to 0, because you can't get anything coming in from outside, you can't release anything to the outside. So everything that happens inside the calorimeter has to add up to 0. So any change that happens here, or any other change, or any other change, they all have to add up to 0. Okay? That's fundamental to the operation of the calorimeter. All right, so that being said, we know that a calorimeter has the ability, even though it's a very good insulator, it has the ability to absorb heat or evolve heat. Not very much, but enough to significantly change the results of your experiment if you do not account for that heat, the calorimeter's ability to absorb or evolve heat. Right? So remember in our lecture, how do we determine the amount of heat that is absorbed or evolved by any substance? Right? the formula that we were using was the specific heat capacity for our substance times how much of it there is. In this time we're using mass. And what's the change in temperature? Right? So the specific heat capacity times the mass times the temperature. And if we consider only the units of measure, just to be sure that this formula will work, we say, all right, what are the units of measure for temperature? Degrees centigrade. What are the units for mass? We're going to use grams. All specific heat capacities that use mass in their formulation are referenced to grams. And then the specific heat capacity would have to be something. But heat is measured in what units? Joules, right? So that has to be joules. That's grams. That's degrees C. So what does S have to be? In order for S, the units of S, specific heat capacity, to give us joules, it needs to be joules per gram degree C, right? That way, grams cancel, degrees C cancel, and leaves us with joules. Okay? So our units of measure are correct. So, the only other variation that you would encounter with this formula is, what do we use here? It depends on what the units are here. If this is specific heat capacity, it's mass. If it's molar heat capacity, then it would be joules per degree C moles. Okay, just change the moles to grams. Now, that would be a different number for the same substance, because moles and grams are related differently for every substance. But in that case, instead of M here, we would have number of moles. Okay, that's the only variation that you will see in this class for using this formula. Okay. So what goes on inside the calorimeter? Well, let's see. For example, if we say Q1 is due to a chunk of iron, and Q2 is what happens to the water when we put that hot iron in there, or the cold iron, doesn't matter. And then Q3 would be what happens to the calorimeter itself, right? So we've accounted for everything that could undergo a temperature change and consequently a transfer of energy in the form of heat. So what if instead of that, we said, well, let me not get ahead of myself. Let's go to the document itself and work through the experiment. All right. When you go to Blackboard, you will find the document, and I'm going to share the screen and show you where that is in Blackboard, just so that there is no misunderstanding. So I'm going to share the Blackboard screen here. Okay, there's our course in Blackboard. And if you go to Learning Modules, and scroll down to the very bottom, you'll see Laboratory Exercises. And then this is experiment number, or exercise number 5, right? There you have the location of the document, and also where you will drop your completed experiment, your formal report. So if we click on that, now, we see, now this is in instructor mode, so it's only going to be previewed. You will be able to, here's the document right here. So if you right click on that and save as, then put it somewhere. And in this case, in my browser, it shows up over here, and you just open that document. And this is what it looks like. Okay. The first thing you have to do is find out something about your calorimeter. We need to know the calorimeter constant. All right. I'll explain that to you in just a second. Then we'll follow up with 3 different parts to this experiment. So we're going to neutralize an acid and a base and find out how much energy is involved in terms of the moles of water produced. Remember, anytime you add an acid to a base, you get a salt plus water. So that we're going to take the values that we get and express them in terms of moles of water produced. Right? The enthalpy of solution of sodium carbonate. So when you put sodium carbonate into solution, is it exothermic or endothermic process, and how much energy is evolved or absorbed in terms of the mass that you put in that water. We'll do the same thing with sodium bicarbonate. Okay, and then we'll have a few questions to answer. And at the very end, we have accepted values, right? So the accepted values for sodium carbonate is here. And this is in terms of kilojoules per mole. Right? So you need to be sure that your units match. This is sodium bicarbonate, kilojoules per mole. And this is the one for neutralization. So this is kilojoules per mole of water. Okay? All right, so that's what the document looks like. Now I need to explain, what do I mean by a calorimeter constant? All right. So if we say that our calorimeter, everything happens inside, is equal to 0, then we can have something else going on in the experiment. Plus, what influence does the calorimeter have? Right, does it absorb energy? Does it release energy in form of heat? What we don't know is the specific heat capacity of the calorimeter. So we cannot use that expression for Q, right? Because we don't know the specific heat capacity of the calorimeter. It's different for every calorimeter. Why? Because our styrofoam cups, manufacturing is not precise enough to make every cup exactly the same. The thermometers are all different, right? So we have to determine a value that is a composite of these two, right? So there is a specific heat capacity, we just don't know what it is. So what we'll do is we'll put those two together and produce a big C, which is our calorimeter constant. Now, what would the values have to be for our big C? Right? In order to cancel degree C, that would have to be on the bottom. Right? And then in order to yield joules, joules would have to be on the top. So the units of measure of our calorimeter constant are only joules per degree C. Right? For every degree change in centigrade, in every Celsius degree change, there's a certain number of calories that can be absorbed or released by this calorimeter. Right? That's our calorimeter constant. Right? So while this expression would be something like that, this one would only be that times that. Okay? And these two don't necessarily, they're not necessarily the same. because the temperature change might be different for the substance inside the calorimeter as opposed to the calorimeter itself. They could be the same, but not necessarily. Okay, so how do we determine the calorimeter constant? That procedure is given on the very first page. All right, here we go, right there. And in order to do that, we're going to take 75 grams, which is equal to 75 milliliters of hot water, and 75 milliliters of room temperature water, and let me pause for a second. Okay, I'm back. So in order to determine the calorimeter constant, we need to set up an equation where the big C is the unknown. It's the only unknown. Then you can solve for it. So again, the calorimetry, everything that happens inside the calorimeter has to equal 0. We've got a change in energy of the hot water, change in heat. We've got a change in heat for the cold, and we have a Q for the calorimeter. Okay? So each one of these is simple enough. It's just the specific heat capacity of water times the mass of the water times the delta T, right? So the change in temperature is always the final temperature minus the initial temperature. And sometimes you get a negative number. That's okay. In fact, it's very important. So we need the final temperature of the hot water minus the initial temperature. And the same thing for the cold water. Now these might be different. In fact, they most likely will be different in terms. And then whatever the Q for the calorimeter is, which will be the constant, times its change in temperature. Okay? So we know what this one is. It's 4.18 joules per gram degree centigrade. Okay? And then mass will be 75 grams, right? Oops. 75 grams. And then the temperature change, all right? So, whatever the temperature change happens to be, and the data that I'm going to give you will give you temperatures for the hot water and the cold water. And I'll just show it to you here. You'll have to print it out yourself from the Blackboard file, which was just below the document. Right? It was a file that was just below the document. We'll give you all this information. And notice, if you can see that, right? The initial temperature of the hot water, in this case, was 75.5 degrees, all right? And the temperature of the cold water was 23. You measure those, right? Right before you put them together in the calorimeter. And then you measure a final temperature, because once you mix them together, the cold water is going to get warm, the hot water is going to get cold, and they meet in the middle at a temperature, right? And you measure that temperature. Okay. So now we know that the initial temperature of the hot water, right here, was 75.5. And the final temperature is the equilibrium position, which is 47.5. Well, let's see. Let's put it down here. 47.5 minus 75.5. 5.5. Right? So that's the hot water change. Notice it's going to be a negative number, right? So the hot water lost energy, right? A negative number means exothermic. So it lost energy to the cold water. Whereas the cold water is going to be this same 4.18, right? And this is coming down here, 4.18. And then its initial temperature, well, final temperature is this. And its initial temperature was 23 degrees, right? Yeah, 23. Okay? It's going to be a positive value because it gained energy from the hot water. How about this one? What is the initial temperature of the calorimeter? Well, the experiment says you start off with the room temperature water in the calorimeter, and you measure it. So the calorimeter has to be the same temperature as the cold water, right? So its initial temperature is also 23. Right? What is its final temperature? I mean, what? No, excuse me. Final temperature is 23. No. Initial temperature is 23. I did it right the first time. Final temperature is this one because it is in contact with both hot water and cold water. When they equilibrate, the calorimeter is going to be exactly the same temperature. So it's going to be the same final temperature as the hot and cold water are. So then all you have to do is say this one, this, resolve this amount right here. So subtract that one, multiply times that, and then this one, that, multiplied times that. We left out the mass of the water. Right, times the mass. And then this one is whatever that difference is. And it sets you up with, and I give you an example of calculations here. In fact, the example is worked out here for you on this blackboard. So you're going to get so many joules from this one, so many joules from that one, and then this one is going to be resolved only for the C value. So in this case, when you solve for C, and I'll let you do that because you're supposed to know algebra already, C in this case is equal to 44.8 joules per degree C. So in our subsequent experiments, you're going to be using the calculator, the calorimeter that you created, theoretically. Remember, you're in the twilight zone. And this value will go into that position for every reaction that you investigate. Parts 1, 2, and 3. The only thing that will change is the temperature change that occurs for that particular experiment. All right, so now we've calculated our calorimeter coefficient, our constant, our calorimeter constant. And remember, when we say it's constant, it does not change. That value is the same from now on, as long as you don't change any parts of its construction. You, if we were doing this hands-on, once you construct that calorimeter, including the thermometer, you don't change it. The thermometer stays in there. You don't use a different thermometer, just that thermometer. If you need to measure temperatures elsewhere, use a different thermometer. Okay, so that's our calorimeter constant. That's identified. That procedure is identified on this data as part 0. Right, see that right there? Part 0. Then the other data that's given in this are by the parts that are actually in the document. There's part 1 for the acid-base neutralization. It's given initial temperature, final temperature. In fact, I even wrote out the calculation. Let's see. That's got a glare on it. There's the calculation right there. Okay. But for the last two, parts 2 and 3, I only give you the raw data because by this time you should be able to do the experiment yourself. Now, what do you do in part 1 when you're trying to express your values so that they can be compared to the accepted values, right? For an acid-base reaction, remember, we're going to put together H2SO4, sulfuric acid, and sodium hydroxide, and it's going to produce sodium sulfate plus water. But we need to balance that equation. All right, so we need 2 here and 2 here. So let's see if it's balanced. Let's see, 2 sodiums, right? 1 sulfate, 4 hydrogens, right? So we have 2 hydrogens here, 2 hydrogens there, that's 4, and 2 oxygens. So there's 2 oxygens there. Not counting these because we counted that as a sulfate, right? All right. So when you set this up and you gather your data, you're going to take 50 grams of acid and 60 grams of base. Let me be sure. Yes. No. It's the other way around. It's 60 acid and 50 base. All right. Actually, that's water. Actually, it's 60 milliliters. All right. And let's see. This is 0.5 molar, and this is 1 molar. Right. Why is that? We'll look at the relationship. The stoichiometry says for every one of these, you need 2 of those. So if we make this one half the concentration of that one, then if we put equal amounts of them together, they will exactly neutralize. Right? But then the question is, why do we put 60 milliliters of this together with 50 milliliters of that? Well, in case you don't remember, whenever you conduct an experiment, whenever you do stoichiometry of a reaction, it's impossible to have exactly the right number of moles of each reactant so that they completely consume one another and produce only product. When you have an exact amount of each one, there's always one that's in the excess and always one that is limiting. Right? So we want this reaction to go to completion, and the only way to guarantee that is to make sure that one of them is in excess at the beginning. So we choose acid is in excess, 60 milliliters versus 50 milliliters. Right? So when you put those two together, there's enough of this one to completely react with that one and produce that much. of water. Okay, so how much water is produced in this reaction? Right? Well, which one's limiting? We know that this one is limiting. So if we find out how many moles of sodium hydroxide, we know that's the same number of moles of water because it's 2 to 2. The ratio is 1 to 1. So if we know the moles of sodium hydroxide, we know the moles of water. Right? So how do you find the moles of sodium hydroxide? Well, molarity, remember, is moles per unit volume. So the moles is equal to molarity times volume. Right? So we just need molarity, right, times the volume of sodium hydroxide. And the units of measure for volume, liters. So we have to change 50 milliliters to liters. Okay? So that means how many moles of sodium hydroxide and consequently how many moles of water have we produced in this reaction. Just 1 times that is 0.050 moles of sodium hydroxide, which is equal to 0.050 moles of water. Okay. So remember, I'll show you the last page again. Remember on the last page, the accepted value here of the acid-base reaction is 57.9 kilojoules per mole of water, minus 57.9. So if we need something that's expressed in terms of joules per mole, we've got the moles now. All we need to do is determine the joules. How much heat is actually evolved. So we know the moles of water. We just need to find out how much heat. All right. So how do we do that? We use a calorimeter, of course. And the method says, which one do we put in the calorimeter first? All right, so we look at it, look at the methods, say which one goes in the calorimeter first. 60 milliliters of sulfuric acid. So the sulfuric acid is going in the calorimeter first. And then we measure the temperature of the sulfuric acid, and that tells us the initial temperature of the calorimeter itself and the temperature of the sulfuric acid. What we want is for the temperature of both the sulfuric acid and the sodium hydroxide to be the same. If it is, that simplifies our calculations. If it's not, it complicates things. Fortunately for you, the class last spring that collected this data were able to determine that the temperature of the base and the acid both, before we mixed them together, was exactly the same. So they started out at the same temperature. All right? So that means we're looking for this one, heat of neutralization. Then there's going to be, that's for the reaction of the sodium hydroxide and the sulfuric acid, as if they were separate from the water. Okay, so they're reacting. Then you have a change for the water. Now, since these solutions are reasonably dilute, 1 molar and a half molar, we're going to assume that the total volume of the acid and the base are water. We know that's not strictly true, but it simplifies the calculation if you consider both of them as of just water. So that means if we have 50 milliliters of one and 60 milliliters of the other, how much do we have total? 110 milliliters, right? So what mass is that? Well, if we're using water, we're going to assume that it's 1 gram per milliliter, which means it's 110 grams. Then we have, what contribution does the calorimeter have, offer to this reaction? Okay, so there we have all our terms. We just need to determine what goes in each one. Well, this one is going to be our calorimeter constant, which was 44.8 joules per degree C, and then its change in temperature. This one is going to be its change in temperature and 4.18 for its specific heat, because we're talking about water, and then the value that goes in here is 110 grams. Okay? So this one, this is a complete term with no subparts. It's going to be our unknown, and it's going to be joules, right? So we know this, we know that. We're going to know this because we measured before and after. We know this, we're going to measure before and after here, and that's 0. We solve for that as our unknown. All right, so that's the heat, the term that goes into our heat of the reaction in subsequent calculations. Right. So all we need to do is measure the temperature before and after. So what is it for water? Well, the initial temperature of the water was 21 degrees. Right? The final temperature of the water we measure after the reaction has stabilized, completed, is 27.5 degrees. Right? So that will be the same temperature change here for that one and for that one. Right. So once you've determined the difference in temperature here and here, you just solve for the heat. Now what do you do with that value? Well, we want to know the Q of the reaction in terms of the Q of neutralization per moles of water produced, right? And we know the moles, we already determined that as 0.050 moles. Then the value you get from here is in joules. So that's going to be joules per mole. But the accepted value is in kilojoules, right? So in order to get kilojoules out of that, you have to divide it by 1,000. Right? So you convert that to kilojoules, right? 1,000 joules per kilojoule, right? Divide by 1,000, then you get your value as kilojoules per mole, and it may have a sign on it. It probably will have a sign, because these neutralization reactions are typically, well, I don't know of a single one that's not exothermic. Right? So when they neutralize, they give off heat. So this value should have a negative sign, and then you compare it to the one at the bottom of that chart on the last page to see what the difference is, and express that in terms of percent error, right? So remember, percent error is equal to the experimental value minus the accepted divided by the accepted times 100. Okay? And then you get your percent error. And that will go into your report, just as all these calculations will go into your report. Right? Even though we're not doing this hands-on, you're still responsible for the formal report. Okay? All right, so that's the neutralization reaction. Part 1. I'm going to erase this because I might need more room. There we go. Okay. So in part 2, we have sodium carbonate being dissolved in water. So what expression, what mathematical expression covers what's happening in our isolated system here? Right? Still equal to 0. Then we're going to have the heat of solution plus the heat change of the water plus the heat change of the calorimeter. Okay? So the water is going to go into the calorimeter first and measure the initial temperature. So that means the initial temperature for this one and that one are the same, as is the final temperature, because they're still in contact. So when they come to equilibrium, the temperature in the final temperature here and the final temperature there are equal. So the delta T's for this one and that one are the same. Right? The only difference is this one, you have your calorimeter constant times that change. And this one, you have the specific heat for water times the mass of the water times the delta T. Right? Right, so what's the mass of the water? Well, the experiment says that you're going to use 75 milliliters of water, right, and approximately 10 grams of sodium carbonate. Right? But it has to be measured exactly, and you need exactly 75 milliliters of water. Right? So 75 milliliters means 75 grams of water, and then 4.18 for the specific heat capacity, and then delta T, whatever that happens to be, based on the data that you're given. This one is still going to be a complete value. It's going to be solved for in joules. And then you'll have to convert it to kilojoules, but what do you divide into it, right? Because all of those terms on that last page were in units of kilojoules per mole, right? So you're going to end up with joules here, and then you have to convert it to kilojoules. But what is the moles? How many moles, right? So we have sodium carbonate, and let's say you're lucky enough, well, what did they actually, 10.046, all right? 10.046 grams was what that class measured. So how many moles is that? You know how to do that. Change grams to moles. What do you need? Whenever you have grams and moles in the same sentence, think molar mass. So what's the molar mass of sodium carbonate? Well, you need your periodic table, right? So what's it's 2 times whatever sodium is, right? What's sodium? Let's see, I have my periodic table here. 23 grams per mole. How about carbon and oxygen? Right? Add those together and you get a value. So whatever you get here goes right there. And you convert this to moles. Then you take that, convert it to kilojoules, divided by moles, and you get kilojoules per mole for this reaction, this heat of solution, right? And it will probably be a negative number. So you should expect to get a negative value here because the reaction is exothermic. All right? That's part 2. Okay. Now part 3 is similar to this one. So I don't have to erase everything. All right. We're going to use the same amount of water. We've got the same calorimeter. We're going to have different changes in temperature because we're dissolving a different compound. The compound in this case is sodium bicarbonate, or sodium hydrogen carbonate is the accepted name these days. Sodium bicarbonate is baking soda. Right. So, how many grams of this one are we going to use? Well, let's see. It's different, I am convinced. It's approximately 7 grams. You get the exact value from the data set that is in the file in Blackboard. So approximately 7 grams. You're going to get a value here. Then you just have to convert that to moles. Same deal. What's the molar mass of sodium hydrogen carbonate? Convert that to moles. Divide it into kilojoules, and you'll get probably a positive value because it's endothermic. Compare that percent error to the accepted value in that chart. And I believe that's, oh, that was part 3. There you go. So part 2 and 3 use the same arrangement here. The only difference in part 1 is this is Q of neutralization, but these are similar terms. All right, let's see what else needs to be done. There were no discussion questions that we needed to go over. You do have some laboratory questions. The laboratory questions, actually the laboratory questions are things that you will include in your calculations and your results and do some discussion. They help to guide you. So in your formal report, if you have a section for questions, you say question 1 and refer to whatever part of the report has that information. Okay. Now, part 4 and part 5, question 4 and 5, they're a little more trouble. I might give you some guidance on those. Okay. So questions 1, 2, and 3, you should be able to complete with what we've discussed up to this point. Question 4 and 5 are a little bit more difficult. All right, so let's take a look at 4. Everybody knows commercial cold packs and hot packs. I mean, if you've ever worked, I have some of my students that have worked as EMTs before they take chemistry. And they know what a cold pack and a hot pack is, as do nurses and maybe doctors. Doctors are not that smart, medical doctors. But nurses know about cold packs and hot packs, right? They come in a plastic bag, there's water in there with a capsule with something inside. And you break it, you mix it together. And sometimes it gets hot, sometimes it gets cold. It depends on what's in that little capsule. So, question 4 asks you to design your own hot pack using sodium carbonate. All right, so if it's a hot pack, it has to be an exothermic reaction, right? If the desired temperature of the hot pack is 50 degrees, how many grams of sodium carbonate must be dissolved in a pack that contains 500 milliliters of water at room temperature? Assume that all the heat is transferred to the water. All right, so we're ignoring the calorimeter constant, right? The pack and whatever's contained in it would be our calorimeter that we would need to determine a constant for. But in this case, for simplicity's sake, we're ignoring the calorimeter. So really what we're looking for here in number 4 is just, right, 0 equals what is what's the heat of solution and what's the heat change of the water. Okay? All right. So to set that up, we need, what's the heat of solution? Well, the heat of solution is going to be joules, but we don't know what that value is yet. In fact, within this term will be the unknown value, right? Because it's asking us what mass of sodium carbonate is required. That's the question. All right, so we need to break out these terms so we can look for mass, right? So, remember what we determined earlier. We determined in part 2 the heat of that solution in terms of moles of sodium carbonate. We want to know mass. But the only term that we have is kilojoules per mole. Okay? So what we need is to say, what does that actually mean? Well, if we're going to have joules as our answer, then we need to have a heat of reaction in terms, actually it's delta H of the reaction, the enthalpy of the reaction. And times the number of moles of sodium carbonate, right? So if this is kilojoules per mole, multiplied times moles, we get kilojoules. And we now have a heat term for this one. Okay? So this can be substituted in there. So what's this value for sodium carbonate? Well, it looks like it's minus 23.3 kilojoules per mole. Now, why don't we just change that to joules? We can do that. Change this to joules per mole, and then it can fit into the reaction here, this formula, with joules over here. Okay? Because this is going to be 4.18 joules per gram degree centigrade. Right? And what's the mass of the water? 500 milliliters is 500 grams. And then whatever the temperature change is, the final temperature is 50 degrees minus the initial temperature, which is 20 degrees. It tells you right there. We want the hot pack to get to 50 degrees, and we were starting at room temperature of 20 degrees. So this is starting temperature, this is final temperature. That's the term. In joules, right? We'll have joules left over here. So if we convert this to joules per mole, then we've got our energy term taken care of within that formula. All right? So minus 23.3 kilojoules is what? Minus 23.3 times 10 to the third joules. Right? Now, that's not strictly speaking scientific notation because, right, we've got that. That's greater than 10. But you can make that correction. So this would be minus 2.33 times 10 to the fourth joules per mole, right? Okay. So we've got this term taken care of. How many moles? We don't know. I think that's the unknown, right? If we solve for the number of moles here, Then we know how many moles of that, but we don't know the mass. But once we find the moles, we can do the mass, right? Because if you have moles and grams, moles and mass, molar mass is all you need to make the conversion. Okay? So if you put -2 here, this term is going to be -2.33 times 10 to the 4th joules per mole. And this is moles of sodium carbonate, right? So there we have 0, we have this, there's our unknown, this is plus. That's all known. We only have to solve for moles of sodium carbonate. And then take the moles of sodium carbonate times, moles, grams per mole, molar mass, and that will give you the answer to this question. Okay? I'm not going to work it out for you. I mean, that'd be too easy. I've shown you how to do it. You should be able to do it now. And also, question 5 is a similar structure, but in question 5, we're using sodium bicarbonate with different temperatures before and after, initial and final. And they want to know how much mass of sodium bicarbonate you need to lower the temperature of your cold pack to 1 degree centigrade. Use the same procedure, same formula, only a different compound. So once you find out the moles, you use a different molar mass. Right? Use a different molar mass to find out the mass after you find the moles. Right? So it's a multi-step problem, but it's doable. We break it down into logical steps. All right. So, when you go to Blackboard, like I'm going to share that again, share that screen again. Let's see, this one. There you go. Now let's back up. There we go. Okay. So, you've got, here's the hard copy document. Here's the data. One other file is going to be there as soon as I get this video converted and uploaded. There will be another file in there with a web link to a YouTube, just like you've used for the lecture part of this course, to view things that we've done in class, in the lecture class. I'm going to do the same thing with this video that I'm creating now, and it will be uploaded and have a link there in this position, just below the data. So you've got everything you need there. You can review the video and take the data, do the calculations that are required in the formal, in the hard copy, and then you can generate your own report. And the due date on that is 17th of April. Right? So 3 from 17 is 14. You've got 2 weeks to complete this and upload your formal document, which will be in this container, right? Right, and here you do attach files. You just browse your computer for the Word document, preferably, or it could be a PDF, whatever. And then you attach that file, and then you just go down here and hit submit. And there you go. You've submitted it. It'll show up in my gradebook. I'll know you've submitted it, and everything will be beautiful, at least until I grade them. Then we'll see how beautiful they are. Since there's nobody actually here, I can't field any questions. But if you do need to get in touch with me, I sent everybody an email. Here we go. I sent everybody an email with an attachment. Actually, that didn't have, yes, here we go. What it had was this this web address right here. So if you want to connect with me via Zoom and we have a video conference, then you need to contact me in advance. Try to keep them on Fridays if at all possible, but they don't have to be on Fridays. The only reason I carve out Fridays is because it's already carved out in my schedule. Fridays, I would normally, right now, I'd be starting up with your class in about 4 minutes on the Logan campus. But since we can't do that now, we can conference. And if you need to get in touch with me by Zoom, then you need to contact me in advance so that I can start a session, and then you can use that address to connect with me, and we can talk. And I can work things out on the whiteboard. I can share screens with you. We can iron out any problems you have. But I'm not going to start a Zoom session and let it run all day long because there are two classes, the 203 and the 213. I'm not going to let it run all day long. So you need to set up a time, or request a time when we can meet, and then I'll start the session. I'll resend you an invitation, right, in case you lose that web address, and then you just copy paste that web address into your browser and click on it, and it will load the client. Usually, sometimes it has to load the client every time. I don't know why Zoom is that weird. Anyway, once we make our connection, then I'll give you an hour, and we'll just iron out any problems. Otherwise, just keep reviewing for each of the exams, going into the lecture, review the lectures, work your review document problems, and then view the review document, and it won't be from this semester, obviously, but it'll be from the last spring semester. From now on till the end of the semester, those videos are available there now for each of the exams that are blocked out. And if any of that still gives you trouble, then like I said, we can set up a Zoom session and iron them out. Okay. That's it for this video, and good luck, and I'll create another video for the next lab. For this class, the next lab will be, here it is, 213. The next lab will be molecular weight of an acid by titration. And that one will be conducted on the 17th. So before the 17th, I think I've got enough lead time now, I'll have another video available, and it will describe that experiment and show you the data that you will use to twilight zone that experiment. Okay, that's it. Goodbye and good luck. Stay safe and healthy.